Welcome back, and I've got another fun experiment to show you today. In fact, it's a collection of experiments. What we're going to be looking at is the electromagnetic spectrum. And then all you do is just put your drink down on the bar and you leave it alone. I'm not sure you expected that to happen, and neither did I. So let's try and explain what's happening. Electric fields apply forces to charges. Why does putting two transparent things on top of each other do something so strange when you turn it through 90 degrees? Leica the dog's not with us again this time. She's off on another one of her travels around the world, and more of that later. So, I've been doing the electromagnetic spectrum and waves with my pupils, and the technician kindly set up some apparatus to demonstrate the different electromagnetic waves. And I thought it was too much of a shame to just clear it all away and not show you. So just very quickly, we're going to have a quick wander through what the electromagnetic spectrum is and what's in it. So I usually begin this topic by getting the students to do a sort of mind map with waves in the middle, and then around it, coming off that, every type of wave they can think of. So they think of radio waves, they think of sound waves, water waves, perhaps what happens in an earthquake. Some of them might know about visible light, etc. And then I say to them, hang on. Cross out all the waves that don't travel at the speed of light. Cross out all the waves that are not transverse waves. In other words, not sort of side-to-side waves where the oscillation is at 90 degrees to the wave travel. Only keep the ones that can go at the speed of light, that are transverse, and more importantly, can go through a vacuum if you ask them to. And what you're left with is all the waves that are in the electromagnetic spectrum. Now, typically there are 7 different types of waves in the electromagnetic spectrum, and instead of just chucking them into a group, what we like to do is we like to put them in an order. And typically we put them in order of energy, low energy up to high energy. And that's the same as putting them in order of low frequency to high frequency, which, if you think about it, is the same as putting it in order of long wavelength to short wavelength. So let's get the 7 waves that my pupil thought about, and let's put them in order of frequency or energy, or in order of ever shortening wavelength. So the first one, the lowest energy, longest wavelength and lowest frequency, is radio waves. We use them for communication, and they're made by a metal antenna with electrons oscillating up and down in the antenna and the wave breaking off at 90 degrees. So radio waves are low energy, transverse electromagnetic waves. So if we increase the energy a little bit, go up in frequency, we go through radio waves from long wave, medium wave to short wave. And when the waves get very short in wavelength, perhaps a few centimetres, we call them microwaves. And rather than get out lots of complicated microwave apparatus, I've just got a dish out to show you that we use microwaves for communications, mobile phones, and particularly for satellite communications. Because what we can do is get the microwaves from a satellite down onto a dish at home, and they focus to a point in front of the dish, and we can pick up that microwave signal and watch satellite TV. So let's go up higher in frequency, shorter in wavelength and higher in energy, and we get to infrared waves. Now, infrared we detect as humans as heat. You can't see the heat. In fact, this at the moment is getting really, really hot, almost too hot to touch, this radiant heater. Just see a little bit of red light sneaking through there, but if I turn it off, it's still very hot to the touch and it's still giving out infrared. Now, we could see that really well if we put on night vision goggles that turn the infrared into visible light that humans can see. We also use infrared for other applications other than heating. They're used in remote controls, and the tiny little LEDs in the front of this give out little pulses of infrared, coded, a bit like Morse code coming out at the front. And though we can't see that, it's that infrared wave that's picked up by the television, and so it knows to change channel. If I hold this in front of the camera lens, if you're lucky, you can just about see these little LEDs at the front flashing. They're sending out an infrared signal to tell my projector in the lab to turn on and off. So we've turned up the frequency, turned up the energy and reduced the wavelength to a really small number, around 500 nanometers, 500,000 millionths of a meter, and we get to visible light. We go from infrared into red light, through the colours of the rainbow, through green to blue, and then finally to violet, the most high frequency of the visible light that human eyes can see. And we obviously use light to light up places so we can see stuff, but we also send it down optic fibres for communication, and I think that should be the subject of another one of my videos sometime. Right, let's go up in energy. Higher than violet, so we're now into ultraviolet, very, very short wavelength and very high frequency. And ultraviolet can be quite harmful. It causes ionisation and can damage the cells in your body. So you have to be a little bit careful working with this. You might have seen what they call the black lights in a disco that make everything sort of glow and shine. And I've done a separate video on that, on fluorescence. But in fact, you don't want to look at one of these for very long because it's not doing your eyes much good at all. Now, ultraviolet's used for a few things, but one of the things it's used for is security markings, and I'll show you that with a banknote. So other than the risks to you, ultraviolet can give you a suntan if you're careful with it, but you certainly don't want large doses. But I mentioned it's used for security marking. So here's a £20 note, and on the top of it is some secret invisible ink, which fluoresces with ultraviolet light. So I'll turn on my black light, my ultraviolet light, and you can probably see 20 coming up there, not visible without the ultraviolet light. And this is a security marking. It's very hard to put on banknotes by people who try to make fake banknotes. So we've made it up to X-rays, very high energy, very short wavelength, and very, very high frequency indeed. And these are much more dangerous than ultraviolet. They can pass through your skin and into the flesh of your body and cause ionisation. So if you're having an X-ray taken, you're fine. But the radiographers that are taking lots and lots of X-rays, of course, will go and hide behind a screen when they take the X-ray to minimise their dose. Most X-rays are digital these days, but older X-rays were taken on film and took much longer to develop. You had to wait to see your X-rays for quite a while. And this one you can see is a chest X-ray, and you can probably see some of the ribs where the lungs are and the spine in the middle. Right, we've made it to the end of the electromagnetic spectrum, and we're at gamma radiation. Extremely short wavelength, very, very high frequency, and extremely high energy, so it's very penetrating indeed. It's different from all the other forms of electromagnetic radiation because it comes from the nucleus of an atom rather than from changes in the electron orbitals. So what we'll do now is have a quick look at gamma radiation and just how penetrating it is. So I've got a source of gamma radiation here. It's in this box, and I'm going to open the box, take the little lid off that I've tipped up so I can get at it, take out the sample, and then I'm going to hold this in front of the Geiger counter, and you'll notice that this radiation travels quite a big distance. Gamma radiation can go quite far, but what's also very interesting is if I take out the little lead-lined box from here, put the gamma source inside, there we go, put the lid back on, and I'm keeping my hands out of the way to minimise the dose, it can still get out through the lead-lined case. So, gamma radiation is the highest energy electromagnetic wave and the most penetrating. So, I'm going to put this away, put it away from myself, so I minimise my dose and it gets safely locked up elsewhere. So, I do hope you enjoyed that video on the electromagnetic spectrum. I'll be making another film fairly soon, and I look forward to seeing you then.